All right, this session is on data quality and starting from what are the different objectives that can be measured here that represent quality of the measurements. So basically, where does the measurement start is from most time from image processing. And long ago, when microarrays started to become available, when people were printing their arrays, this was due to background problems, dust, and movement of spots. And we had different measures of that. Not many people are doing that, but there are a number of manufacturer-specific quality measures that says how well each individual probe behaved in the experiment. So this is just to illustrate that there is probe-level measurements for QC that you need to consider. And but what's most commonly done is on a particular array or sample. In array CGH, you define good quality where you have neighboring probes that don't change much. So if you look here, where you have very small changes between the neighboring probes, this is a good example of a good sample. And a bad sample is where you have big, giant steps between neighboring probes. So how do you quantify that? So pretty much every manufacturer has some variations that quantify that probe variance. So for example, Agilent uses the DLRS score, or derivative log-to ratio spread, which is the standard deviation of the difference between adjacent log ratios. And they do remove the 50% interquantile range probes that fall beyond that as outliers. Because, of course, any sample that has copy number changes does have big steps in it, and you want to remove those. Affymetrix uses the MAPD score, which is the median absolute pairwise difference, which is median of the differences. So it's, again, a robust method. And then the next is quality score, which is the variance of the difference between adjacent log ratios, but it excludes certain outliers. So if you look at all of these, they're all doing very similar, not exactly the same, but very similar measurements of how much variations you have in neighboring probes, but also accounting for real copy number change. So here's a toy example I put together in Excel, creating 30 probes and showing an area here that is representative of a copy number gain. So what we want to measure is like how much noise is here while ignoring these big changes that have to do with the real copy number change. So here are the 30 points, and here is the difference between the neighboring points. So here, this 0.18 is how different these 2 points are, 0.125 and 0.02, so it's a small difference. So if you take all of these guys, and this one is, of course, the big difference here, 0.6 is where a real copy number change has occurred. So if you take all of these numbers and calculate the variance, so you just in Excel type in variance and calculate that, it's 0.02. And some of this variance comes from these big changes that have to do with the real copy number event. So what you could do is you can sort all of these and then take the top X%. In Nexus, the default is 3%, but let's say in this example, we'll take the top 10%, so these 3. So we'll remove these big events, so that removes these 2 events that have to do with the actual copy number change and another big, probably noise event here. And now we calculate the variance, and this is 0.002. So this is what we call the Nexus Robust Variance QC, and that's the number that you see being exported within Nexus. So here's an example. So for this real-life example, this is a sample with a QC score of 0.012, and that's with a 3% outliers thrown out, and then here's gets a QC score of 0.224. So again, this is the Nexus QC is just one measure, but all of them are trying to look at the difference between profiles. So one thing to consider, because people always ask, is what should be a good cutoff for the QC? One important factor is it's very platform dependent. So if you look at these two samples, they come from the TCGA, so it's the same sample run on two different platforms. I believe the left one is Illumina and the right one was Agilent. And if you look at the numbers, well, the QC score of this one is a lot higher than this one, so it must be more noisy. But in reality, if you look at this gain, this trisomy here, you can see the signal for that is at around 0.4, and on this one, it's around 0.2. So different platforms have different dynamic range aspects. So, for example, the Agilent has a higher dynamic range than the Illumina, so it can give you a bigger QC score just because of that. It doesn't really reflect anything having to do with this being a poorer quality than this one. So I hope that that is clear from this. So the conclusion here, before one additional comment I want to make on this is, and just measuring how much variation you have is only one aspect, because in a sense, if you have a very flat line here, that could be because it was a bad hybridization and you really have no signal, even though there was some changes there. So the conclusion is that you should really look at the sample QC measure as one of many different ways that the quality can be assessed, and probe level QC should not be ignored. So if you have access to that level data, you should certainly take advantage of that. And the QC measure should always be compared within the same platform. And finally, visual inspection is really what you need to do. So I would like to show just very quickly some example of this in this live presentation. So I'm using this project because it has data from different platforms, including Imaging, which was an Agilent arrays, Affymetrix, and Nimblegen, and Illumina. And you can sort the data in this project based on the quality, and you could see that the lowest value is this array, and the highest one is this one. So let me just select these guys. And since they're sorted based on quality, this should be the best quality sample. So if I click View, the top one here gets the best score, and the score, quality score here is 0.02. And if you look at the variation, there's still a bit noisy in my view. But let's go down to the last one here, and you can see this one is quite a bit more noisier. And this almost looks like just pure noise. Now, what I wanted to show was this other one, which is the next worst, noisiest, where you can see that there is the trisomy 18 that's being detected. And this goes back into my point earlier, that even though the quality score on this array is pretty bad, and the spread is very bad on this very old array, but if we're looking to identify big events like this trisomy 18, that's certainly discernible from even this level of noisiness. But should you trust some of these other smaller events that might be getting called here, like this gain there, as well, this is probably not something trustworthy. So you could get rid of some of the smaller events by changing the significance threshold as well, but just want to make sure that that is in mind. So this is the end of the QC session.